We're going to use a comparison test to determine whether or not this integral converges or diverges. So my first inclination, now that you can see this is improper because this is 1 to infinity, my first inclination is to compare this to the integral from 1 to infinity, 1 over e to the 3x dx, or you can rewrite that as 1 to infinity of e to the minus 3x dx. So now I'm going to integrate this guy here to see if he converges or diverges, and then determine whether or not that will be helpful in determining the convergence or divergence of this guy. So the first thing you do when you're doing an improper integral is you write your limit. The limit is b goes to infinity in this case of 1 to b e to the minus 3x dx. I'm going to use substitution on this. U equals minus 3x, du equals minus 3 dx, 1/3 negative du equals dx. So that tells me that my limit as b goes to infinity. Now I'm converting to u, but this is still an x. X equals 1 to x equal b, minus 1/3 e to the u du. Integrating that, this is a limit as b goes to infinity of minus 1/3 e to the u from x equal 1 to x equal b. Substituting all the variables for x back in, I have the limit as b goes to infinity of minus 1/3 e to the minus 3x, 1 to b. Now using the fundamental theorem, which is the last step I do use before I actually take the limit, minus 1/3, I plug in b first, e to the minus 3b, minus 1/3 e to the minus 3. That's what I actually want to take the limit of. So, in taking the limit of that, I have to think, okay, what happens if b gets larger and larger? Now, this is just a constant. Just a constant. But here, as b gets larger and larger and larger, this negative power becomes more large negatively. But the negative power actually means that this is a denominator. So, for instance, what I mean is, I can rewrite this as limit as b goes to infinity of minus 1 over 3e to the 3b plus 1 divided by 3e to the 3. That's simplifying what's in the square brackets here to the square brackets here. That's a little easier to take the limit of at this point. So as b goes to infinity, this guy gets larger and larger and larger. That means the whole thing goes to 0. So my limit looks like it's equal to 1 over 3e to the 3rd, and so therefore it converges. Now, if this integral converges, then that integral converges. And if this integrand can be shown to be smaller than this integrand, thus this integral being smaller than this integral, then we know we can prove convergence. So what I have to make sure of, I have to go up a little bit here so I have space. I have to make sure that when I graph these, this is the one that I calculated was convergent from 1 to infinity. So I need to make sure the other one is somewhere below it. This has got to be 1 over e to the 3x plus 4 in order for this to work. So I have to prove this first, and everything comes out in the wash. Prove this algebraically. You can't just put it on a graph and say, oh, look, it works that way. So if I'm going to work on my proof here, I'm going to prove that the integral of 1 to infinity of dx over e to the 3x plus 4 is less than the integral of 1 to infinity dx over e to the 3x. If that's true, I can be equal to, if that's true, then both of these converge because this one converges. So let's think about a proof. All right, I know that e to the 3x is equal to e to the 3x for all x greater than or equal to 1. This is my proof. Don't mix this up. Now, if I add 4 to this side, how does that change the comparison for x greater than 1? Well, this is going to be bigger. If I take the reciprocal of both sides, we know from arithmetic that changes the direction of the inequality sign. And from this point, we can say that the integral from 1 to infinity of 1 over e to the 3x plus 4 dx is less than or equal to the integral from 1 to infinity 1 over e to the 3x dx. So from this, since the integral from 1 to infinity 1 over e to the 3x dx converges, so does the integral of 1 to infinity 1 over e to the 3x plus 4. And there you have it.